Hello, everyone. We move on to study lecture 5 in module 2. Module 2 is about the study of the background knowledge behind the design of a robot's body. Before we enter the study of lecture 5, let's have a quick overview or quick review about the learning objective of this course. The learning objective of this course is for you to become a designer of a robot as a product. And as a designer of a robot as a product, you must know the answer to these 4 questions. Question number 1, who are the user? Question number 2, what are the needs of a user? Question number 3, what are your robot which could meet the need of your user or future buyer? And question number 4, what are the solutions behind the design of your robot? By now, you should know the answer to question number 1 and the question number 2, because in manufacturing and the society, there are many users. And the generalized need from this user is to have a motion provider. And you know that the robot are good candidate to serve as a motion provider. Therefore, your focus should be on the study of answer to question number 3 and then question number 4. And based on the specific need of your future user or future buyer, you must know, okay, what should be the functionality of your robot which could meet the need of your user and the buyer. And in particular, you need to know what should be the solution behind the design of your future robot. And therefore, you need to know how to draw out the detail of the blueprint of your future robot. And this slide gives you a general guideline about the key aspect behind the design of your robot. And these key aspects include hardware aspect of your robot and the software aspect of your robot. And in particular, you can see the presence of module 1, which is about the design of a robot software. You also see the presence of a module 2, which is about the design of a hardware of your robot. And you also see the presence of a module 4, which is about the design of a software aspect of a robot's control system. And also you see the presence of a module 3, which is about the modeling of your robot in terms of kinematics and the dynamics. With this knowledge in mind, you should be able to design the physical body of your robot, implement the software of your robot, and also to develop or implement a digital twin or simulator of your robot. Okay, so therefore, in order to draw out the detail of your robot's blueprint, then you need to study all these topics which have been categorized into these 4 modules. For example, module 1 will enable you to design robot software. Module 2 will enable you to design robot's body. Module 3 will enable you to design the digital twin or simulator of your physical robot. And module 4 will enable you to design the software aspect of a robot's control system. Okay, and here I give you additional 5 questions to think about, and hopefully these 5 questions will will help you to focus your study and help you to pay attention to energy flow, signal flow, knowledge flow inside your robot, and in particular to know what should be the relationship between energy flow and the signal flow, and what should be the relationship between signal flow and the knowledge flow, right? So now we enter the study of lecture 5 in module 2. So this will be the last lecture in module 2 or for the study of module 2. By now, we have already studied the background knowledge behind the design of a robot's brain, the background knowledge behind the design of a robot's mechanism, and the background knowledge behind the design of a robot's actuator. And in lecture 1, we have studied the system aspect of a robot because we consider robot as a combination of many systems. Okay, so inside this system, we can identify 3 of them which play the key role. Okay, inside the body of a robot. These 3 key systems include a robot's mechanic system, a robot's control system, and the robot's programming system. Okay, so the focus of module 2 is for us to study the hardware aspect of these 3 systems. Okay, for example, a robot's mechanic system must include appearance, mechanism, and the structure. So therefore, you see lecture 3 is for us to study the background knowledge behind robot mechanism, all right? And the robot's control system must include the hardware support in terms of robot brain, robot actuator, and the robot sensor. So you will see lecture 2, 4, and 5 are for us to study the background knowledge behind the design of a robot's brain, robot's actuator, and the robot's sensor. All right, and for the programming system inside your robot, and the programming system need the support from the hardware aspect of a robot's brain. So therefore, so immediately you understand, okay? Module 2 basically provide, okay, the hardware support to module 1, module 3, and module 4. All right, so this help you to understand the relationship among these 4 modules. Okay, in terms of learning outcome, so you will see module 2 enable you, okay, to design the physical body of your robot. Then module 1 will enable you to design robot's mind or robot software. Okay, and module 3 will enable you to design and develop the digital twin or simulator of your physical robot. And module 4 will enable you to design robot's control system. Right? So now I hope that you will have a clearer picture about this roadmap of learning. Okay, so inside module 2, then you see the presence of lecture 5, which is about the background knowledge behind the design of a sensor. Okay, from the study of lecture 4, okay, the last video that you have seen, in which, okay, you see the feedback control loop, and inside the feedback control loop, you see the presence of a sensory feedback. So therefore, we must make the robot's body to be ready, okay, in order to support the implementation of a robot's control system. And the sensory feedback is one of 3 basic building blocks of a control system. Okay, so these 3 basic building blocks include controller, system under control, include actuator, and the sensory feedback. Okay, all right. So then for lecture 5, we will follow, okay, this outline. So first we want to know, okay, or to be convinced, okay, by the need to incorporate sensor inside the body of a robot. And then we will look okay, this aspect of sensory motor interaction, because of inside the human body, we have a lot of such scenario or example of sensory motor interaction. Okay, then we are going to study the background knowledge behind the design of a motion-related sensor, which include position sensor, velocity sensor, acceleration sensor, force torque sensor. All right, and another important aspect of hardware support to the implementation of a robot control system is this brain sensor interface. Okay. So here I will provide you additional material for you to do self-study, and our recommendation for you is to make use of a Cortex M series microcontroller. All right. So let's start with the introduction, okay, or the background knowledge about the sensory motor interaction. And based on this concept or this knowledge, immediately you understand, okay, sensor play a very, very important role for the achievement of controllable motion by robot, okay? So then this video is a typical example of sensory motor interaction, because the action taken by the motor is under the guidance or under the interaction, okay, achieved by sensory feedback. So you see we have a vision system to provide positional information to the robotic arm. Therefore, the robotic arm could control the motion of the actuator in order to achieve this type of behavior. So this is a typical scenario, okay, of sensory motor interaction. Okay, and this is another example showing you the scenario of sensory motor interaction. All right. And then this slide basically highlight to you, okay, the scenario of a sensory motor interaction, because inside the robotic arm, we have a sensor, and you see, okay, because for each robotic joint, okay, we will, in normal case, incorporate link joint, torque joint, and the power joint. And behind the power joint, then you will see the presence of a sensor, okay? So then with this scheme of a hardware design, then this robotic arm is ready to support, okay, the implementation of a sensory motor interaction. All right. So therefore, then you see sensors are very, very important, okay, to be present inside the body. And because without the sensory feedback, then we cannot, okay, design a robust feedback control system. All right. So, and this slide basically show you, okay, the typical example of a sensor, which is already included, okay, together with motor. Okay, so here you see we have a actuator. This is the power joint. Behind the power joint, we have a sensor. Then the real example is like this. So this is a power joint, and this is a velocity sensor with the capability of outputting position information. Once we take out open up this optical encoder, okay, incremental encoder, then you will see the inner component inside this sensor. So you will see there's a rotating disc. Then we have a reading device to read out the optical pulse. Then inside here, we also have the electronic circuit, then output the signal, digital information through all these pins, right? So then, and this picture show you what is inside the reading device. So actually, we have a light emitter and a light detector, okay? And then you see we have all these dark pattern and the light pattern, okay? So light can pass through the light pattern and will be stopped by the dark pattern. Okay, so then in this way we can read out the signal. All right, so that means this one basically illustrate what is inside the signal reading device. All right, okay. So this is just a typical example, okay, about the optical encoder. All right. Then for constrained motion, because robot can carry its hand or tool to perform a motion in a three-dimensional space. And when there's an interaction between the environment or due to the gravitational force, okay, then this robot is undergoing or performing constrained motion. And the typical example is this one, okay? The robotic arm carry a tool to perform a milling process, okay? So then you see there must be an interaction force between the workpiece and the robotic arm, okay? And in this case, the robot carry a tool, and this tool has a certain weight, okay? And then there's a gravitational force acting on the robot hand, okay? So then in this case, there is an interaction between the gravitational force and the robotic arm, all right? So in general, the interaction between a robot's hand and the environment could be described by a torque vector and the force vector. So for torque vector, there are three components. So you have a torque about the three principal axes plus force with the three components along these three principal axes. So we can put them together. Then we have an interaction vector which consists of 6 elements, right? So obviously we want to measure, okay, what is the actual, okay, interaction vector between robot's hand and the environment, all right? So previous slide show you the motivation for us to incorporate sensor into the body of your robot. And the reason is we want to implement sensory motor interaction behavior, okay? For example, the feedback control loop, it could be feedback control loop for position control, feedback control loop for velocity control, feedback control loop for force torque control. All right, so these are the typical example of sensory motor interaction. And in order to achieve a sensory motor interaction, the presence of a sensor is necessary. All right, so I believe by now you are convinced by the need to incorporate sensor inside the body of your future robot. Okay, now we are going to study a few cases, okay, and in which we are going to learn the background knowledge behind the design of some typical sensor in robotics. Okay, so we start with position sensor, and in particular we use this absolute optical encoder to serve as an example for us to know, okay, the background knowledge behind the design of a position sensor. All right. Then this video showing you the working principle of absolute optical encoder and the design guideline for you to come out a similar design solution.
Rotary absolute encoders consist of a translucent disc with a binary pattern etched on it. The pattern consists of a series of opaque and transparent slots. The slots are arranged in a concentric circular fashion, and the number of slot sets is the same as the number of photocells used in the encoder. A light source is located on one side of the strip, while photocell detectors are placed on the other side. The rotary absolute encoder shown here has 3 sets of slots and hence uses 3 photocells. As discussed earlier, with 3 photocells, an absolute encoder can detect 8 unique positions. In other words, the full shaft rotational angle of 360 degrees can be divided into 8 angular intervals of 45 degrees each that can be uniquely detected by the encoder. Here is another view of the 3-bit rotary encoder. If a more accurate measurement is needed, then an encoder with more data bits can be used. As discussed earlier, this means using more photocells in corresponding circular slot sets. Typical rotary absolute encoders have 8 or more photocells. The encoder disk shown here is from a rotary gray code 8-bit absolute encoder.
All right, so the video basically show you the working principle of absolute optical encoder, and the video also show you the key element inside the design of absolute optical encoder. Okay, then this slide basically give you a summary about the knowledge that you have seen from the previous video. So in short, we have a rotary disc. On the rotary disc, we have different the circular parts like the track. Okay, on the track we have a transparent area, opaque area. So this is kinds of a coding. Okay, then we have a light source which will emit the light. Then we have a photocell to detect the incoming light. Okay, so the light can pass through the transparent area inside the disk. Okay, and the light will be stopped by the opaque area in the disk. Okay, so therefore, for one circular track, basically it will output one series of a signal from one photocell. If let's say we have a 5 photocell, then this position sensor will output 5 bit. Therefore, because the 5 bit, either each bit will take the value 0, 1, then we have a total combination of 32 position. So 360 degree by 32, then you will know the accuracy of the measurement. That means each position will correspond to this angular position, which is equal to 360 degree divided by 32. Okay, because this is an illustration for an absolute encoder with 5 bit as output. All right, so this is the working principle, and also, okay, this is for you to understand the key element inside the design of absolute encoder. Okay, so here I'll give you some more example. This is a 3-bit absolute encoder. Okay.
You get the function of an absolute rotary encoder, as well as the principle of a multi-turn encoder. Rotary encoders are also named as shaft encoder. Measuring systems which use this type of encoders can be classified as indirect and digital. The absolute encoder has a coded disk. As an example, you see here the binary code. The construction of an absolute encoder is more complex compared to an incremental encoders, as they require a decoder. But the big advantage is that each angular position of the shaft can be read at any time, even after a power failure. That means there is no counter value to lose. Counting the number of revolutions with a multi-turn absolute encoder. This example shows a 2-stage multi-turn encoder with its main components. The animation begins. For counting the numbers of revolutions, an internal reduction gear is connected to the drive shaft. The measured value is therefore composed of the angular position and the number of revolutions. Depending on the numbers of revolutions, which has to be counted, more gears with its coded disk can be added.
All right, so this is this is another example. Okay, so we're showing you the detail about the design of absolute encoder with 4-bit sensory output. Okay, so with a 4-bit sensory output, therefore we have 16 combination of a position. Okay, because 4-bit, each bit will output 0, 1, then 4-bit will give us 16. Okay, distinct position counted from 0 all the way to 15. All right, so then you will see. So this is a design for the disk. So you have a transparent segment, opaque segment, etc. For position 0, then you will see then the light can pass through all the segment 0, 0, 0. And for position 1, then eventually the sensor will get the output, which is equal to 0, 0, 0, 1. For position 2, then you will get the digital output, which will be 0, 0, 1, 0. For position 3, then you will get the digital output, which will be 0, 0, 1, 1. Okay, etc. So then in total, we should be able to obtain 16 sensory output, which indicate 16 distinct angular position, right? And if let's say we want to increase the number of measurable angular position, then we just increase the number of digital output. And this is example of design with 5-bit sensory output. So therefore, because with the 5-bit sensory output, the total number of a combination will be 32. Then we can measure position from 0, 1, and all the way to 31. Okay, because for position 0, then you will see the output will be 0, 0, 0, 0, 0. Okay, for position 1, the output will be 0, 0, 0, 0, 1. Then for position 2, the output will be 0, 0, 0, 1, 1. All right. Okay, so this show you the detail about the design of absolute encoder with 5-bit of data as output. And if let's say we increase the number of bit from let's say 5 to 8, then with the 8-bit inside the output sensory data, then we should be able to measure 256 position, because 2 raised to the power a equal to 256. Okay, so the position is counted from the position 0 all the way to the position 255. All right, so then with this type of sensor design, then you will understand. So we must have the photocell or the phototransistor, because phototransistor means these are the photocell. Okay, so therefore, so we have 8-bit as in the output. All right, and we also have a light source, and eventually for each photo detector or photocell, it may have its own dedicated light emission diode, or light source. So that means for each bit, it will have like its own dedicated light source. All right. Then this is just a simple exercise for you to practice, so that you know the parameter which are related to the absolute encoder with 8-bit in the output of a sensory data. Okay, so if let's say we want to know what is the total number of a measurable position, the answer should be 2 raised to the power 8. Then you get this value 256. Okay, if let's say we have this reading of 0 position, then what should be the reading of 0 position? So by default, so it makes sense for us to name the output, which is 0, 0, 0, 0, 0, 0, 0, 0, to be the 0 position. The first position, which is measurable. Okay, now we want to know, what happens if this disk, rotate at the absolute orientation of 45 degree. Then this is the angular position of 45 degree. Then what should be the reading from this sensor? Okay, so then the answer will be because the resolution of the measurement is equal to 360 divided by 256. Okay, so then if we let the 256 divided by 360, so this gives you the resolution per degree, okay, the number of a bit, okay, the bit value per degree. So because in total we have a 360 degree, then for each degree, what should be the value output, the sensory data, the value, okay, from the sensory data, okay. Since now we have a 45 degree, then 45 times this resolution, then we will give you the output value from the sensor. So then you do this calculation, which is the 32. Then 32, you convert it into binary number. Then you have a 0010, 0000. All right. Then we continue. If let's say, and the angular position is 135 degree, because the resolution per degree is equal to 256 divided by 360. Okay, because this number gives you the output, the sensory data or sensory value per degree. And we now have 135 degrees. So you time them together, then you get this decimal number, 96. Convert it into the binary number, then you have this answer, 01100000. All right, so this is just a simple practice for you to know, okay, the relationship between input and output, okay, inside this sensor, okay. And this video show you color, okay, design detail, okay, for position sensor.
Announces the arrival of the world's first fiber optic position sensor.
And all optical design makes it 100% immune to any electromagnetic interference. Micronor's novel fiber optic position sensor consists of a sensor and a controller. The system is connected by a duplex fiber optic cable. No electrical connection to the sensor is required. There's one fiber optic strand for transmitting light to the sensor and one fiber optic strand to receive the light with the position information from the sensor. A push-pull fiber connector makes connection to the controller simple. An LED status indicator confirms that the connection to the sensor is completed and that the system is functioning properly. The model MA4825 is a true absolute position sensor with an incredible resolution of 13 bits. Or transmits a burst of light to the sensor. Inside the sensor, a code disc modulates the spectral components of the light. The position information is now imprinted in the optical spectrum of the light and guided back to the controller for position readout. The system keeps accurate track of positions and speeds in excess of 2,500 RPM. This is an absolute position sensor. Single turn with a 360-degree continuous reading and a resolution of 8,192. It keeps track of speeds in excess of 2,500 RPM.
So you see, this is a very accurate position sensor, because you see this sensor is able to measure 8,192 discrete position. Okay, and in addition, in the early part of this video, you see the design of a disc. The pattern on the disc is different from the previous example. Okay, so this is why you could be innovative in the design of the rotating disc. All right.
To demonstrate that this sensor is truly absolute and capable of giving accurate readings at startup, We will now power down the system and start it up again. First, note the position readout of 1,457. The field below shows the angle calculated in degrees. Now, we unplug the fiber optic cable, shut down the software, unplug the power to the controller, and remove the serial interface cable. To start up the system again, we plug in the serial interface and restore the 24-volt DC power to the unit. For now, we leave the fiber optic cable unplugged until the readout software is running. While the sensor is disconnected, the maximum readout of 8,191 will appear. Now, we reconnect the optical fiber and the readout will return to the 1,457 position.
Okay, this observation is very important for you to know. Okay, with the absolute sensor, then once you power off your robot, robot will memorize the position. Once you power on, immediately you get the right reading about the actual angular position of your robotic arm or robotic joint. Okay. However, with the most industrial robot, we never use absolute encoder due to the cost consideration, and we use incremental encoder. Okay, so that is a sensor for us to measure velocity. Therefore, once you power off your robot, then you power on your robot again, you totally lost the knowledge about what is the actual angular position of each joint. Therefore, you must make some movement in order for this robot to recover the zero position of each joint. And this operation is called as a homing. So for those of you, if you have experience in operating industrial robot, then now you understand how come every time once you power on your robot, you must do the homing. All right, the reason is because inside the industrial robot, there is no presence of absolute encoder. So therefore, with this feature, you can imagine, okay, why not to incorporate absolute encoder inside the design of industrial robot. Then in this way, you do not need to do the homing operation. Okay, today's practice is like that. Okay, we do not use absolute encoder in the design of an industrial robot. We use a velocity sensor. Right. So this is just for you to know. Okay, if you let me see, increase a little bit the cost, and who knows, maybe one day the cost of absolute encoder will drop. Okay, once you incorporate absolute encoder, then you do not need to do the homing because you can turn off your robot and turn on your robot immediately. You know, okay, the initial angular position for each joint. All right, so this is something for you to know.
The sensor will always know its exact position, whether the shaft is stationary or rotating. The controller is powered by a 24-volt DC and consumes only 70 milliamps. Numerous position output interfaces accommodate many applications. The sensor is unaffected by electromagnetic interference, lightning strikes, electrical discharges, energy weapons, magnetic fields from motors, and radiation. The positional information is embedded into the light spectrum and not the amplitude. Thus, it's unaffected by a varying loss in the fiber optic lines. This wave graph shows the reading of the sensor. When the optical power changes, as simulated here by adjusting the connector, one can see a drop in the readout waveform. However, the position reading is not affected at all. Rather than using light intensity, Micronor ingeniously utilizes the light spectrum as an information carrier, making this a very robust position sensor. Again, note that the position readout does not change when the light amplitude is brought back to the previous level. The MR330 is an absolute position sensor, immune to electromagnetic interference. It will not radiate or spark, and operates reliably with fiber optic cable lengths of up to several hundred meters. So when true position is needed, micronet is the solution.
All right, so this video show you an innovative way to design the rotating disc or the pattern on the rotating disc. All right, so and then of course you may have other way to design position sensor. For example, use a potentiometer. So this is a low cost sensor for the measurement of absolute position. And the working principle is to relay the output resistance to the position of the viper, because the viper is a moving element. It will move with a robotic joint, okay, or other moving link, okay. When this move, then the output resistor will change. If you supply a current, then the output voltage will change, okay. And then this is a relationship, okay. The current equal to input voltage divided by the total resistance. Then this current times the output resistance, then give you the output voltage, okay. So this is for linear motion. If you have a rotary motion, therefore then the total resistance is equal to the length times 360 degrees. And if let's say this is actually rotated angular position, so then the theta times L is proportional to the output resistance, all right? Then L cancel out, and then you have this relationship. So you will see the output voltage is the function of rotated angle, all right? So, and in our project, so this is the result from our project. So we use a potentiometer to serve as a sensor inside the finger, because inside the finger of a robotic hand, we have a limited space, okay? So, and the actual size of a potentiometer is like the button of our clothes, okay? So it's very, very small. Therefore, we can place such a small position sensor inside robotic hand, all right? So this is just the background knowledge for you to know about the design of a position sensor, all right? And then how's about velocity sensor? So you remember, for motion-related physical quantity, we could identify position, velocity, acceleration, and the force torque. Okay, so therefore, we want to know, okay, how to design velocity sensor. Then here I use this example to serve as a case study for you to know the background knowledge behind the design of a velocity sensor. And this one is a very popular one in robotics industry. We call it as an incremental optical encoder. So basically it's a velocity sensor, all right? And this video show you the working principle of incremental optical encoder.
Encoder, also called a shaft encoder, can be used in positioning and motor speed feedback applications. In this video we explain the function of an incremental rotary encoder. Measuring systems, which use this type of encoder, can be classified as indirect, digital, and relative. Incremental rotary encoders use disc which contains transparent sections that are equally spaced. A light-emitting diode serves as transmitter and its light is detected by a photodetector. Therefore, the encoder can generate a sequence of pulses. The output is measured in pulses per revolution, which can be used to determine either the position or the rotational speed. To detect the rotation direction, the encoder needs two tracks. The sense of rotation determines which signal coming from track A or track B is leading. Here you see the signal form coming from clockwise rotation. Here you see the signal form for counterclockwise rotation. Now the signal coming from track B is leading. Thanks for watching this video.
All right, so then this slide summarizes the working principle and the key element inside the design of a velocity sensor. So from this picture, you will see the key element also include light source and photocell. and also include a rotating disc. Okay, and however, in this case, you will see the simpler way to design the disc, because in total we only have 3 tracks. Okay, so you have a track A, track B, plus a reference track for the indication of a 0 position. All right, because this sensor will not only output velocity but also position. All right, so this is why for industrial robot, in order to save the cost, we use this type of a sensor to be incorporated inside the power joint. Okay, so therefore, in order to know the positional information, we must do the homing. Homing means what? To get this signal, to get this reading. Once we get this reading, then we know we are at the 0 position. Because once you power off, then you power on. So this 0 position will be totally lost. All right. So you need to do the homing, then find all the reference position for all the joint inside your robotic arm. All right. So this is a key element inside the design of a velocity sensor. All right. And for this sensor, because basically it output angular displacement. Therefore, we need to know what is the amount of angular displacement plus the direction of a rotation. So this is not like the case of a position sensor. Position sensor, we directly get the reading of the position. Okay, 10 degrees, 16 degrees, that's it. Okay, but for this one, we only know the displacement. Okay, displacement of 5 degrees. Then we want to know whether the 5 degrees is counterclockwise or clockwise. So therefore, we need to know this information about the direction of motion. And this is why we need to have track A, track B. And then you will see the track A, track B has a phase shift of 90 degrees. Okay, it's a 90 of electrical degree. Okay, so it's like this. The misalignment is about the 1/4 of period. Okay, because we treat entire period is 360 degrees, then 1/4 is 90 degrees. All right, so based on this offset, then the signal output from track A, track B will have offset in phase. Then we can talk about whether signal from A will lead signal from B, or signal from B will lead signal from A. Based on these two information, then we know whether this disc is undergo clockwise rotation or counterclockwise rotation. All right, now you understand why do we need to have these two tracks. And this one is for us to know what is the 0 position. If let's say we start from a 0 position to do the integration of accumulated displacement, the result is what? The absolute position with respect to the 0 position. All right, so then you already have an overview about the working principle of this velocity sensor and the key element inside the design of velocity sensor. All right, then we have this terminology which is called as a pitch angle between two adjacent holes. So basically, if it's on this disk, we have 100 holes, then 360 degrees divided by 100, then the pitch angle will be equal to 36 degree. Then we have a microcontroller. Okay, this is why now you see the interface between sensor and the robot brain is very important, because you need to leverage on that interface to read out the sensory data. All right, so assume we have a microcontroller to count the number of pulse, because each pulse indicates the rotated angle of theta p. If the count number is equal to c, then c times theta p is the total rotated displacement or angular displacement. And if this angular displacement divided by duration in which this angular displacement occurs, then result is average angular velocity. All right, so this is the way for us to determine the reading from this type of a sensor. All right, so then this slide summarizes the design requirement. So basically on the disk, we must have a 3 track for track A, track B, and track Z or I or R. So this is serve as a zero position tracker. Okay, for us to know where is whether we reach this reference zero position or not. Okay, so reference means a zero position. All right. Then for each track, we have one pair of a light source and photocell or light detector. Okay, and then the electronic circuit may looks like this. So this is the light source. Then your disk is here. When the light can pass through, then this like this transistor will switch on. When you switch on, then the voltage at this point is 0. And assume this is an inverter. Then okay, if this is 0, then you get the 1 as the output. So it means when light pass through, then you get the 1 reading. Okay, for some electronic circuit, they may not have this inverter. Then it means when light pass through, you get a 0. When the light has been blocked by the disk, then you get the 1. Okay, so it depends on the detail. Okay, in the design of electronic circuit. So this detail is not important. You just need to pay attention. That's it. Okay. So important thing for you to know is we must have a light source. We must have a photocell or light detector. Okay. We must have a rotating disk. This rotating disk must have a 3 track. Okay. So a real product is looks like this. Okay. From here you will see, hey, how come we do not have a 3 track which is present to here? Okay. And that this design basically is to achieve a similar outcome instead of having the offset, okay, between track A, track B. We can play with the pair of light emitter, light detector. So make the pair of light detector, light emitter have the offset, and also you see play with the position of this reference track. Okay, so this is another way to design. So that means because everything is relative, either you align all this together, then you create the offset here, or you align the disk together, very simple disk with very regular pattern. Then you create the offset among these 3 pair of light source photocell. Okay, create the offset. Okay, among these 3 pair of light emitter, light detector. All right, so mathematically it's equivalent because everything is relative as long as there's a relative offset or shift in the phase. It's good enough. But this illustration will help you to understand. Okay, it's more intuitive for students to learn. Okay, but this is more efficient for engineer to design and produce the product. Okay, so. But mathematically, they are equivalent, exactly equivalent. All right. For example, in order to know, okay, how to detect the counterclockwise rotation, then use this illustration or design, and it's easier for you to understand. Counterclockwise rotation means rotate in this way. Okay. Immediately you see the hole from track A will reach, assume this 3 pair of light emitter, light detector are aligned together. So immediately you see this hole will appear, okay, between light detector and the light emitter first, followed by B. So it means what? Signal A will lead signal B. So this is why signal A will lead signal B. Then conceptually, immediately you understand, okay? When signal A leads signal B, okay, then the rotation is counterclockwise, okay? Then how about clockwise rotation? Then we rotate in this way. When rotate in this way, then immediately you see the hole on the track B will first enter, okay, the path between light emitter and the light detector, or let the light to pass through. Then the track B will first emit a signal. That means signal B will lead signal A. Therefore, the disk is undergo clockwise rotation. Okay, so conceptually, this design will help you to understand. All right. So then for the linear motion, but actually this one help you to understand this design principle. So we can make the pattern to be uniform. So you have an opaque segment, transparent, segment, opaque. Okay, then we create the offset among these three pair of light detector, light emitter. Okay, and this example basically illustrate you okay, about now this is offset, okay, between these two pair of a light emitter, light detector. So you see they are not aligned together. So then the lace offset, and this offset is just equal to 90 degree of electric angle. All right. So then you have opaque pattern, transparent pattern, and if let's say this disk now is a linear disk, okay, undergo motion from left to the right. Okay, so from left to the right, then you will see this is a transparent pattern. So you will see transparent pattern will first enter the path, okay, between the light emitter and the light detector, which belong to signal B. Because signal B here underneath, you just imagine you have a light detector, a light emitter and light detector. So this will enter the path, okay, between light emitter and the light detector of signal B. So therefore, signal B will lead signal A. So you will see you have a transition, rising edge followed by rising edge from A. If this one move toward the left-hand side, then you will see for this transparent pattern. So you will, this one will first reach the path between light emitter and the light detector of signal A. Okay, then signal A will lead signal B. Then we know this is a linear translation toward the left-hand side. Okay, so this help you to understand. Okay, what is the design inside here? So immediately you can imagine. So there is an offset between the light detector and the light emitter of signal A and the signal B. All right, okay. Then based on this observation, so actually we can summarize some rule to guide the programmer to program to develop the software which automatically make a decision about the direction of the motion. For example, when B lead A, then this is a clockwise rotation. When A lead B, then it's a counterclockwise rotation. Okay, so this should be quite straightforward. All right, then how about the change of the direction? So you move, then suddenly, okay, you undergo counterclockwise rotation, then you change and then move in the clockwise rotation. So then you apply this rule, this is observation. Okay, when one signal undergo two transition, let's say a transition from low to high, high to low, another signal remain unchanged. If you see this situation, or like this case, let's say signal B remain unchanged, but the A make two changes, then this corresponds change of motion direction. Okay, so you can use this rule to make your sensor smarter. All right. So again, you see you need to have a sensor brain interface because this decision rule could be implemented inside the robot's brain. All right. Okay. So then this is just a simple practice for you to know what is the pitch angle between two adjacent holes. Let's say we bunch, okay, 200 hole, okay, inside the rotating disc. When the disc make a full rotation, then we will see 200 pounds from electronics. Then we ask you to know or determine what should be the pitch angle from this sensor. So answer will be 360 degree divided by 200, then result is 1.8 degree, all right? So here it means when you have a counter to count all these powers, so then each period correspond to 1.8 degree, all right? And one more example, for example, if let's say you have a velocity sensor and inside angular displacement between two adjacent hole is 1.8 degree. If the sensor output 500 pounds within this amount of time, then what should be the average angular velocity? Okay, then you apply this formula because you observe 500 pulse. Each pulse corresponds to 1.8 degree, and the duration is 10 milliseconds. So you convert to second 0.01. So this is the degree. If you convert it into radian, you must times pi divided by 180 degrees. Then you get this answer. Okay. So the average velocity is 1,570 radian per second. Okay, so it is very fast rotation. All right. Okay. And then for linear motion, so it's similar. Okay. So we have a linear displacement, which is 0.1 millimeter. So this is a linear displacement between two adjacent transparent pattern. Okay. And if the brain of your robot, let's tell you within 1 second, okay, I observe 7,000 count, then what is the linear velocity? So then, okay, so you just, because it is 1 second, you see this amount of count, that is 7,000 times this value. So you must convert all this to meter, all right? So then the linear velocity is 0.7 meter per second. All right, so this is just a simple exercise for you to play. And this one is just for you to think. So it means actually in this area you can do innovation. For example, for absolute encoder, conventional way to design the pattern on the rotating disk is to have the same number of track as the number of which is equal to the number of photo detector. Okay, so for example, if you have a photo detector, then you create a track. If you have a 13 photo detector, then you create 18 track. But that is a challenge. If you increase the number of track here, and the manufacturing or production of such a device require a very, very high precision. Okay, could we reduce the complexity? And from this design for velocity sensor, you see it's quite simple. We only have a 3 track. Okay, regardless of what is the dimension of the disk, just 3. Then could we combine advantage of both? Then the answer is yes. Okay, so we still maintain the capability of this velocity sensor for the measurement of displacement, because we only need to know what is the zero position. Because for this one, you see, we only have one pattern to indicate this is a zero position. Then in order to search for this zero position, you need to rotate at least plus minus 180 degrees. So there is a big movement on one plus minus 180 degrees in order to find this hole. All right, can we improve it? Then the answer is yes. So instead of just create a single pattern on the track, reference track, actually we can place many patterns. Okay, let me just rotate a little bit. Immediately we know what is the actual position. Then we treat this position as a zero position. All right. So this is this innovation. Then detail is explained here. All right. And in the last video, you see this incremental encoder with or the absolute encoder with 13 bit as output. So more or less looks like this. Okay, it's not exactly like this. Okay, so it's quite similar to this one. Okay, so this gives you an idea about the area in which you can undertake okay, innovation in the design of a pattern on the rotating disk. All right, so that is for you to think about. All right, okay. Then the next issue is, by now we know how to measure velocity, how to know the direction of a rotation, then how to make this sensor to also output positional information, because in the control of a robotic arm or robotic leg, okay, we may want to undertake a position control. Therefore, we need to have sensory feedback from the position. Okay, so then by default, we add in this reference track. Okay, and depends on the textbook. Some Sometimes we name it as a Z, we name it as a I, so I or Z. So it's just for you to be familiar with all this notation because there's no international standard in robotics to standardize the notation. Therefore, you must be familiar with different notation. Okay, so you just understand the requirement of the knowledge. Okay, so implementation, detail, and eventually you can use your own notation. All right, Z means 0, I means why not use R? R could be reference. All right, so Z maybe is better, 0 position. Okay, that indicates 0 position. Okay, now you see in this illustration, people use I. Okay, so I basically indicates 0 position. Okay, or here they say this is an index for 0 position or 0 point. Okay, but Z maybe is more intuitive. All right, so this is a solution. So that means as long as we rotate the disk until this signal appear, then we treat that one as a 0 position. So at that position, we must remember what is the count, because once you power off your robot or power off your power on your sensor, you do not know what is the start position of the sensor. Okay, then you start to rotate. Okay, then your counter will start to count. Okay, once you get this signal as output, so you must memorize that value reading from the counter, and is the reading of the counter at the 0 position. Okay, so you must remember, because then once you rotate again, what you get the reading is an increment from previous value in the counter. All right, so you need to pay attention to the meaning of the reading from the counter. Okay, so then this slide help you to understand all this relationship. Okay, so this is by definition. For example, we want to measure what is the absolute position with respect to this reference position. Okay, so this is a reference or 0 position. Okay, so this is a definition: current position minus 0 position divided by duration in which this angular displacement occurs. This is by definition. This is from sensor's reading. Okay, so this is the pitch angle from your sensor. This is the reading from the counter. This is the reading from the timer. Okay, so actually they have the same meaning. So then you equal these two definitions together. So this is a definition. This is from a sensor's data relationship. Okay, now you cancel the data t. Then you let express theta equal to 0 position plus this increment of the position, okay, and which is measured by the sensor, okay. So now we rotate this one, okay, until the 0 position emit a signal, okay. Then you reach, this is the 0 position, okay. So you reach there, okay. So then you memorize the reading from the counter when the index I or Z emit a signal. So it means this sensor is at 0 position. Okay, so you must remember this value. Okay, so now you have this equation. Now you let this one minus this one, compute the subtraction. So this one minus this one, then immediately you see you remove the initial position when you power on your sensor. So this is the initial position. With this value we do not know. Okay, once you power on, then you are at this position. Okay, what is the reading? We don't know. Okay, so then we manage to cancel it out. Then we have this equation for us to calculate the positional information with respect to the 0 position. Okay, so then this is the actual reading. Then when C equal to CR, you get the 0. Then when C is equal to any value, then you get the absolute position with respect to this 0 position, right? Then this exercise help you to understand the use of this equation, okay? For example, this is we power on the sensor and let the sensor to rotate until we find this I signal or Z signal, okay? Then at this time, we store the reading from the counter. So in this case, it's a 615, okay? We memorize it. now we let the sensor to rotate. If they say now the reading from counter is this one, now we want to know what is the absolute position with respect to the reference zero position. Then you apply this to calculate. The answer is a negative 3,000, okay, 312 degree. All right, so this this measurement is very, very powerful channel because you can do the measurement beyond 360 degree. So this is the advantage compared to the absolute encoder. You remember absolute encoder only allow you to measure zero position to 360 degree. If you go beyond that, then the reading become 10. Let's say 370 degree is equivalent to 10 degree, John. Then you do not know, okay, whether it's a 10 degree or 370 degree, etc. But for this one, no problem at all. Okay, so it is absolute measurement about the positional information, right? So this is the advantage. So then we continue. The third type of sensor which are related to motion should be acceleration sensor. And here we are going to study the background knowledge behind the design of a 3-axis accelerometer. All right. And this video show you the working principle and the key element inside the design of accelerometer. Okay.
The acceleration sensor combines two components in its housing, a signal processing chip and the actual micromechanical sensor. This cone-like structure is the characteristic feature of such a sensor. The blue part of this structure is movable. This part is deflected during acceleration and deceleration. The result is a change in the capacitance between the electrodes. This change is measured by the signal processing chip and converted into an output signal.
All right, so this slide basically summarizes the content which has been shown in the video. So you have two parts. One is a sensing part, another is electronic circuit part. Electronic circuit part means interface with robot brain, because for microcontroller, normally there's a support for you to do the signal acquisition, signal processing, etc. Okay, so we focus on the sensing part. So sensing part consists of inertial mass, spring, and the sensor's body. The spring is to bring the inertial mass back to its nominal position. Okay. Then we also have this sensing axis. So if you have a 3 axis, then you must have a 3 perpendicular sensing axis. Okay. So this sensor can only sense acceleration along this axis. Okay. For example, we have acceleration toward the left-hand side, then the inertial mass will shift toward the right-hand side. When this shift, then you see we have this variable capacitor. Okay, so here we have two. So we have two fixed outer plate and one movable plate. Okay, so in this scenario, you see the gap between these two parallel plates has been shortened. Therefore, capacitance will increase. Then for this capacitor, the gap has been increased. Then capacitance on the left-hand side will be reduced. Then we have this relationship. Okay. Then once we have a circuit to measure capacitance and this change, then we can do a calibration. By calibration, then we can relay the reading of capacitance to the reading of acceleration. Okay, so then this slide basically summarizes the design of working principle and the key element inside the design of accelerometer. All right. Now here show you more example. Then you see this is the inertial mass. Then you see all these presence, okay, of capacitor. You have many, okay. This is also a capacitor, and then this is a spring, okay, which will restore the inertial mass back to its nominal position. Okay, so And then you will see the basically design guideline is you have an inertial mass, you have a spring, you have a sensor body, then electronic circuit, something like that. And then one more example, then this one is a 3-axis accelerometer, because this sensor element allow us to measure acceleration in Z along Z axis. Then these two allow us to measure the acceleration in X and along X and the Y axis. Then the measurement circuit, this gives you some idea, okay? Usually you have a pair of capacitor, it's like here you are in pair. Then for this pair of capacitor, you can have this type of measurement circuit to amplify the signal. And you will see this is an alternative current circuit, and we do not supply sine cosine function. Instead, you see square wave form. So this could be positive and okay, because this is alternative, so here could be 0, 1, 0 volt, 1 volt, here also 1 to 0, okay? And if you apply the background knowledge from a Fourier transform tell you any signal is a sum of a pure sine function. So actually, this means what? Instead of supplying a single sine function of a voltage, so this is equivalent to say we supply many sine function of a voltage. Okay, you should not say there's no sine function in the input. Actually, it's not. It's you have many sine function at the input, because this waveform is equivalent to a combination of many sine function as an input. So therefore, so this is a typical example of a multiple input and multiple output circuit. Okay, so then for each sine function, you should be able to calculate what is the impedance and then determine what is the output voltage. Okay, then since you have many sine functions, then the output is the sum of them. That's it. All right. So this just help you to understand, this measurement circuit. All right. So then this is the exercise for you to practice in order to know the simple mathematics behind the design of an accelerometer. For example, this is a single axis accelerometer, so which allow us to measure acceleration along y-axis. Okay, so then you will see we have an inertial mass, we have a spring, then we have a sensor body, which is not shown here. The spring will maintain the inertial mass to be at the nominal position with respect to the sensor's body. Then here you see we have a pair of a capacitor. Here we have another pair of a capacitor. Okay, so when there is a acceleration downward, okay, gravitational acceleration, for example, okay, downward, then this inertial mass will shift upward. Okay, then this capacitance will increase, this capacitance will reduce. Okay, then we can measure, okay, the reading, okay, from this sensor. Then assume in this case we know the mass of inertial mass, okay, which is 0.1 g, and the spring constant is 1.8 nu per meter, and the sensor body will undergo acceleration, gravitational acceleration, okay, 9.8 meter per second square. Then what should be the displacement? Okay, nominal displacement is 0, and then what should be the displacement? Because this is a spring, assume displacement in y direction is theta y times spring constant, mass equal to the inertial force. Okay, inertial force equal to the mass times the acceleration. So once you have this equality, you put in the value, then you can calculate what should be the displacement by the inertial mass along the y-axis. All right, so it's just a simple exercise. Okay, so actually you can use your handphone to verify this result. Okay, so this video show you the example of the experiment with your handphone.
While my phone is resting, we have an acceleration value in the z direction. That's because gravity is actually affecting the sensor. And as you might know, gravity is 9.8. So we're getting a value of 9.4, which is pretty close. So just keep in mind that gravity also affects the value of your accelerometer. So let me move the phone around just to show you how it changes the values. So that's the application. Let's go ahead and take a look at the code.
All right, so because every one of you, I guess, have a smart handphone, then actually you can play with your smart handphone. All right. Then this one show you application of accelerometer to prevent such accident, or to use this sensor to trigger the release of the airbag. Okay. Then you see the airbag come out. Okay, has been released. All right. All right. So then, okay, by now we have already studied the background knowledge behind the motion related to sensor, which include position sensor, velocity sensor, acceleration sensor. Then there's one more important sensor in robotics, which is the force torque sensor, because your robot should be able to undertake constrained motion. We will study the scenario of constrained motion in module 4. By now, you just keep this concept in mind. When robot interact with the environment, the robot basically perform a constrained motion. Therefore, we must have sensory feedback from a force torque sensor in order to measure what is the actual value of interaction between your robot and the environment. So therefore, force torque sensor are very important in robotics. All right. And this video show you the working principle and the key element inside the design of a force torque sensor.
We're scientists, right? That's our job. And so data is everything, and reliable data, repeatable data, that's paramount. And so if we have a sensor we can't trust, it undercuts the whole process. So we need to have data we can trust, and we have sensors we can trust.
That quality has to be perfect if we're depending on the robot to do its job correctly every cycle, day in, day out, year in, year out.
One of the things that makes robotics really function is repeatability or precision. What the force torque sensor from ATI gives us is both accuracy and repeatability.
The force torque sensor is a device that uses silicon strain gauges and converts mechanical loads into forces and torques, and it measures simultaneously in all 6 axes, force XYZ and torque XYZ. When you look inside the ATI force torque sensor, you can imagine it resembles a wheel with an outer wall, an inner hub with spokes or beams connecting them. Each beam has 4 silicon strain gauges that function in pairs to.
Okay, here you see the key component inside the design of a force torque sensor. So you have an outer rigid body, inner rigid body. These 2 rigid bodies are connected by 3 beams. On each beam, you will see at least we have a pair of strain gauge, okay, which are placed on 2 adjacent surfaces. So you have another pair and another pair here. And we have electronic to read out the resistance value from each strain gauge. And we have another electronic circuit to process the data, combine them together, etc. All right. So you see these are the key element inside the design of a force torque sensor.
Form half bridges. The output of the transducer is 6 channels of strain gauge voltages. The output is digitized and then converted to force and torques through a matrix calculation. ATI uses very sensitive silicon strain gauges to maximize gain, greatly reduce.
And eventually here you may see, because each beam has a 4 phase, then for this version, you see each phase we have a strain gauge. Okay, so that means in total we have 3 times 4, 12. All right, so in practice, but in theory, Okay, for simplicity, then we can say for this beam, we only have a 2, this one has a 2, this one has a 2. Then in total, we have a 6 because we just need to have a 6 output. Then from 6 input, we should be able to produce 6 output. So this is just for learning purpose. So in practice, nothing prevents you to have a 4 for each pin. Then therefore, in total, you have 12, all right? Okay. But actually, you can say I can combine the reading from this one, top and the bottom together, treat them compute the average, and the left and the right treat them as a composite strain gauge, and then combine the reading together. So it's up to you. All right. All right.
Reducing signal noise. The high gain in the strain gauges allows the beams to be extremely strong, providing very high overload protection. Proprietary bonding methods used during the mounting of the strain gauges greatly reduces hysteresis, which can be a problem for load cells.
The benefit of using a force torque sensor versus a single axis load cell is that you get a complete picture of everything acting on that transducer instead of just one snapshot of the measurement.
The ATI sensor can measure loads that are applied in any orientation on any axis. ATI force torque sensors can.
Okay, so this is a typical scenario of doing constrained motion because there is an interaction between the two robot's tool or robot's hand and the workpiece. Therefore, you must have a force torque sensor to measure what is the actual interaction between the tool and the workpiece.
Stand overloads between 5 and 20 times the rated measurement range.
As a robot company, we have to be ahead of the curve, or try to be ahead of the curve. The good thing about ATI is they are ahead of the curve. Their force torque sensors are rated well beyond what the robot is spec'd at for payload. Let's say, for example, communications protocols and buses, ATI always seems to be right on line, right on track with what the industry needs at a particular point in time. So we don't really have to spend a lot of time asking ATI for features and functionality.
Our customers all have different environments where they need to use our sensor. So we have developed interfaces to work in every one of them, whether it's NetFT, which will communicate Ethernet data, or DAC-FT for connecting to data acquisition hardware, or the controller FT for standalone operation, and even our newer wireless FT and EtherCAT FT.
This product is being used in every major university in the United States and throughout the world. It's also used in every major manufacturing facility around the world.
The force torque sensor allows them to provide robots with a sense of touch, a sense of feel, that allow them to do applications normally done only by humans.
The most important thing force torque sensing gives us is the ability to open up the robot to other applications where we normally wouldn't have that ability.
Some of the more common applications for force torque sensors are product testing, life cycle testing, control of robots for surgery.
The robotic technology with the full 6 degree of freedom of control gives you a lot of freedom that you never had before, because you need to be able to measure 3 forces, 3 torques to get the full loading state of any joint. And that's true for any joint. Once you establish that, you establish the full loading state of any specimen of any joint you want to do.
The coolest thing by far that the force torque sensor is being used for are groundbreaking applications, doing things that no company has ever done before. When we work with our space-related customers, or we work with people doing microsurgeries, things that haven't been invented yet. And we're able to be a part of that process and go through the journey with them to develop their product. Really, whatever the customer needs, ATI is able to provide.
So the support I get from ATI is really great. They have all these products, so it's really nice. That's kind of a one-stop shop. So if we're using ATI and have no reason to change, it's a good product, so we keep using it.
Coming from manufacturing myself, I know the importance of reliability and uptime. When we order a product from them, everything comes complete. Software, cables, hardware, take them out of the box, and we're up and running in 20 minutes.
We like using ATI force torque sensors here at ABB because of the robustness, first of all. They are proven, they've been validated by us and by the customers. Customers know them by name, they have a reputation.
Our trust at ATI has to be the highest possible because the quality and performance of the ATI product and its reliability is a direct reflection of how well our robot can do its job each and every time. And ATI is absolutely a critical part of that.
With the continuing innovation with ATI and their engineers at the facilities, they are not stopping at what they have today. They're continually looking to meet and exceed customer expectations today and for tomorrow's use.
Reliability of the force torque sensor is extremely important to ABB because our name is on that robot. We have to have very reliable end-of-arm tooling, and ATI gives that to us with their force torque products.
All right, so then this slide basically summarizes what you have seen in the video about the working principle, about the key element inside the design. And then from here, you see that this is another way for you to design force torque sensor. So you have outer body, inner body, and these two bodies are being linked by these 4 pins, and each pin must have at least one pair of strain gauge. Okay, so when there is a relative interaction between inner body and the outer body, then the beam will undergo microscopic deformation, and this deformation will either compress the strain gauge or stretch the strain gauge. So then when there's a compression, the resistance will be reduced. When there is a tension, then resistance will be increased. So by measuring the variation of resistance, then we can relay the reading from the sensor element to the actual interaction. Okay, and then after calibration, then we can have accurate measurement about the force and the torque. All right. So in general, a torque is a vector with 3 elements, and the torque is also a vector with 3 elements. All right. So then when we put them together, we have 6 values. So we have an interaction vector, which consists of 3 elements for force and 3 elements for torque. All right. So these are the summary about the design working principle and the design detail inside force torque sensor. And this is one more slide. We show you the property of a strain gauge. Okay, so on the tension, the resistance of a strain gauge will increase. On the compression, the resistance of the strain gauge will reduce. Okay, so therefore, when we place the strain gauge on the beam which connect 2 rigid bodies together, and when there is an interaction force, then okay, the strain gauge will change its output resistance value. And if we use the Wisdom bridge circuit to measure the resistance of each strain gauge, then we should be able to get the reading, okay, about the variation of the resistance from each individual strain gauge. Okay, so this is quite straightforward solution for us to do the measurement. Okay, basically convert resistance to the output voltage. All right. So in the video, you have seen the design which make use of a 3 pins to connect inner body to the outer body, and assume on each pin we only have 1 pair of strain gauge. Therefore, we only have 6 reading, because for each strain gauge we must use its own Wisdom bridge circuit. So in total we have 1, 2, 3, 4, 5, 6 Wisdom bridge circuit. Then therefore we have 6 output, 6 reading. Then we can relay this 6 reading to the 6 unknown. Then by default we just use a matrix. This is called as a calibration matrix. Okay, if we follow this design example in which the inner body is connected to the outer body by 4 pins, and each pin has 1 pair of strain gauge. Therefore, we will have A reading. Okay, from this A, the strain gauge. Then we can use this matrix to map, okay, the sensor reading to the true value of force vector and the torque vector, okay? So this is called as a calibration matrix, okay? So in practice, you can treat the 0 as another element, okay? So a coefficient, so that means by a calibration process, then we will know this matrix. Once we have this matrix, then we have the sensor, which should be output the exact value for force and torque. All right, so this is a mathematical detail about the calibration of a force torque sensor. All right, then this video show you the application with the force torque sensor, and for the scenario of doing testing, doing programming or whatever. You see, this is the testing result. Okay. So then this is the output, the torque, okay, about the y-axis. Then this is the testing with the possible application. This is to do assembly with interaction as a feedback, then automatically adjust it, okay, motion control. So this is a typical example of a hybrid control. So you control the motion and also control the interaction. All right, so it means force torque sensor will enable you to undertake a constrained motion in which there is an interaction between your robot and the environment, or between your robot and the human operator. Just now in this video, you see the human operator can use his hand to move a robotic arm. Okay, so that is a typical scenario of interaction between the human being and the robotic arm. All right, so that's all for lecture 5. So the key takeaway is for you to understand the importance of incorporating sensor inside the body of your robot. In this way, you will make your robot to perform a controllable motion. And then we have studied the background knowledge behind the design of a motion-related sensor, which include position sensor, velocity sensor, acceleration sensor, and force torque sensor. Okay, one important aspect of sensor module is to have this built-in capability of a brain sensor interface. Therefore, I provide you extra material for you to study in order to understand okay, a little bit of detail okay, with regard to brain sensor interface. Because the full study of this aspect require another semester, and we have another course which cover Cortex M series microcontroller. Okay, so by doing self-study with this material, then you have a basic idea about this capability for your robot to have. All right, so now we are ready for you to study module 3, because module 2 has already teach you robot mechanism. Then use robot mechanism as a background knowledge, then you are ready to study the relationship between input motion, output motion, and relationship between motion and the force torque. Okay, so that should be the focus of module 3. And also you are ready to study module 4, because the hardware support to module 4 will be actuator, sensor, and microcontroller. Okay, so module 2 provide you the background knowledge about the control systems, the hardware. Therefore, in module 4, you just focus on the software aspect of the robot's control system. All right, thank you for your attention.